Our next speaker comes from Paris, France. His name is Dr. Georges Labrie. He's a professor at the École Nationale Supérieure de Télécommunications. Sorry if I didn't pronounce that properly. I don't speak French. He also works for the French National Electricity Company. And he's going to talk to us today about a pretty hard problem to deal with very long time series where you have very wide gaps. And how do you do interpolation? And when you do this interpolation, estimate the error. And this is very relevant to problems we have here at UC Berkeley in astrophysics, because we have very big gaps. And we also have measurement error in our observations. So many of us here are interested to see this applied to a different problem for photoelectric cells, for solar cells. He's going to talk to us about how to predict power generation given variations in sun and cloud cover and in a sensor network, so that you can sort of share power. A pretty cool project. So I'll give the floor to him. Thank you.
Thank you. Can you hear me? Is it okay? So first I want to thank the organizers to give me the opportunity to present this work here. This is joint work from Télécom Paris, which is an engineering school in France, and EDF, Électricité de France, which is the main electric power company in France. So the motivation of this work is that, as mentioned Joao, there is a trend to introduce more renewable energy in the power network, mainly solar panels, PV, photovoltaic PV systems, and wind farms. So this is a problem for the power network because the production of electric power is subject to huge variations with time. As you can understand, if there is sun, there is production by PV system. If there are clouds, the production goes down very fast. So this is related to the smart grid problem. In the smart grid, one important thing is to introduce renewable energy resources in the grid. So there is a need to be able to predict what's going to be the production of renewables in a short term, I mean a few hours, and more locally, I mean in a region or in a city. So the goal is to build develop a method for very short-term predictions of individual PV system. I mean here one site of a solar panel. There are several approaches to do so. First, the main approaches do not deal with prediction for individual sites, but usually there are methods dealing with a region and a longer term, for instance, prediction 1 day ahead, more aggregated and longer term. And these methods use usually external information, which is a weather forecast, for instance, if there's going to be clouds or not. There are approaches which try to use the same approach for more local prediction and shorter term. The problem with these approaches is that you need to acquire locally weather forecast information, and up to now the weather forecast information is not very good locally because it's interpolation of larger forecasts. Another approach to do local prediction is to track by satellite images to track the movement of clouds, and then by processing these images, try to find if a cloud is going to arrive at a certain point or not. So this is interesting, this is under development, and again, it needs a lot of computation and to acquire locally this information about is a cloud going to arrive or not. So we do not want to compete with all these very good approaches, very complicated approaches. We try to build a more simple approach, which is not going to be the best one, and it's not going to give the best prediction. But the idea is that we consider a set of local sites, each one having solar panels, and we try to predict locally what's going to happen in a very short term regarding to prediction. So we do not require any external information about weather forecast. We just work on history of prediction within within each site, but we allow some collaboration between the sites if they can help each other for improving the prediction. So the outline of the talk is, first I'm going to describe quickly the method, then tell a few words how it can be deployed in a real environment, then give the results of some experiments on real data. So the method is based on what we call local analog search, which is a kind of k nearest neighbor method. Then we try to find within each site which are the situations in the past which are more similar to the current situation. So each site stores, keep track of the history of its own production. So we have k nearest neighbors. Then we have a second step. We define a collaboration which enables to select within these k analogs, this k most similar situation, to select only B situation using this collaboration. And then we run the prediction. Actually, it's a little more complicated because it's real data. So we need to have a normalization phase before applying the learning algorithm, and then before prediction, we have a denormalization phase. Just a few words about this normalization. As you know, the production of solar energy is subject to changes during the day, depending on how much sun there is, if there are no clouds. So we just divide the real production by what we call the clear sky production, which is the production without any clouds, and which can be computed from the history of the site. So we work on this signal. Then we have this local analog search. So we define a template, which is from the current situation, which is a number of previous timestamps where we recorded the production. So we store from the current situation, we have the description of the current situation in the terms of some previous production. And then the problem is to try to find, to predict the production in what we call the horizon. So the system is very simple. We look for past situations using this same template and a similarity measure, which is the Euclidean distance. Remember, we have normalized the curves. So we find in the history several situations. Actually, we select k analog situations. We can associate weight to each situation depending on the similarity to the current situation. So what's important now is that we have selected some timestamps in the past with some weights associated with each timestamp. So we do this within each site. Now we have this collaboration process. So the idea is that each local site does the same job, look for the analogs in the past, determine the different timestamps, and the weight of each situation for each selected timestamp. Now they are going to collaborate. So the collaboration is very simple. The different sites do not send any information about the production, but only the timestamps of the k most similar situations and the weights of the situations associated with each timestamp. They only exchange timestamps and weights of timestamps. So this collaboration can capture not everything, we'll see at the end, but what we call a current global climatic situation. I mean by climatic, I don't know, situation, some situations which we observe frequently in the past. So, as an example, here we have this current global situation, and this site has found two analogs, this analog and this second analog. And for this site, there are two possibilities. It's going to be sunny in the next hours, or it's going to be cloudy in the next hours. The idea here is to define this collaboration so that the other sites may have to select this analog instead of this analog. So how does it work precisely? So we are currently working on this on site I, and site I has found 4 analogs at these different timestamps. The other sites, the neighbor sites, have found as well analogs but at different timestamps. So this analog, we look at this timestamp and we find that there is only on site 3 which has an analog at the same timestamp. For the second analog here, there is no analog in other sites at the same timestamp. For this one, there is one, but for this one, as you can guess, this one is going to be the winner because there are several timestamps, analog timestamps, at the same time within other sites. So this is how the method works. So once we have selected, so first for each site, we have selected K analogs. From the K analogs, we have selected only B analogs, a subset of them using collaboration. Then we have these B analogs, and we use the horizon of the previous analogs to make a prediction. So we have B proposition for the next future, for the prediction, and we compute after the denormalization, we compute a median curve to do so. So this is the method. So it's interesting to see that it's very easy to scale it to a very large number of sites by using a peer-to-peer approach. So each site can contact a server module and register to this server module. And once it has registered, some neighbors are defined, and then the collaboration can work using this peer-to-peer approach. Note that the production of each site is not shared between servers, only the timestamps. So then each site can do its own prediction using this collaboration approach. Another feature, if some sites agree to give their production, historical production, it can be used by neighbor sites which are just installed. So new sites may benefit from the history of production of other sites. So now I describe some experiments we've done to assess the quality of the prediction. So if you remember, I said it's not going to be the best method and the best performance. So we considered data, real data from 2 years of production of 11 PV systems in the island of La Réunion, which is close to Madagascar. We have time series either at 10 minutes or hour step. But that data has been normalized with respect to clear sky production, as I explained to you. We use 1 year for learning and the other year for assessing the performance. The similarity measure is the Euclidean distance, k is equal to 50, b to 25, and we have worked on horizons of prediction of different lengths. We have worked on, of course, it's important to compare this with competitive models. So we considered first model we call the persistent method. So the idea is that at current time we have some production. Then in the next 30 minutes, it's going to be the same production. So this is the persistence model. It's a little corrected by the clear sky model. So we use the shape of the clear sky curve to adjust the persistence model. So this is first reference model. Then we use another reference model. The idea there is to be able to do collaboration. So we used a linear regression method. So for each site, we have its own history of production, and we build a regression model. So it's an auto-regressive model, predict the next value from the W previous values. So what we did is we have regression model without collaboration, and if we consider collaboration, it means that we are going to use previous values of other sites. It means that data is centralized. You need to centralize data to build these models. And it means that the data is shared between the different sites because you need to transmit this data. So some results. So first, shortest horizon, 10 minutes. So what we can see, so we have here the results for the 11 sites. For each site, here on the left part, we have the performance, so it's a mean square error of the analog method in blue without collaboration, in red with collaboration. So first thing, if you consider all the sites, we have a slight improvement using collaboration. Then the second, the next method here is the persistence model, and then we have the linear regression model. Here it's without collaboration, and here it's with collaboration. So the results are regression models are better than the analog method. For regression model and for analog method, collaboration helps a little, slightly. Then the reference model of persistence, which is completely trivial, is between them. So this is for the 10 minutes. For 30 minutes, we see the trend that the persistence model is going to be worse, degrades. But still we have the same results for the linear model is better than the analog model for all sides, and collaboration helps a little. For 2 hours, the persistence model is really bad. And here we have only the analog model, which the linear model is still better, but there is a slight or no improvement with collaboration. So, it's good news, bad news and good news. I think that if the fact that collaboration does not degrade the result, first, it's good news. It's a slight improvement. Then we have only here 11 PV system, only 11 sites. So we are working on a larger number of sites, 250 sites. We just had some data about this. And we hope that it's going to help, collaboration is going to help more when we have more sites. So, as a conclusion, we have proposed a collaborative analog method for predicting PV generation locally at each site. It does not generate the best possible prediction, but it does a good job in a simple way. It uses only PV production data, no external information on weather forecast. It keeps locally private the production values between sites, even if there is a collaboration. The collaboration, there is the exchanges, the communications between sites are very, very small, only these timestamps. And another feature is it can be applied to other sensor network problems, for instance, for temperature or for wind, and even we can have heterogeneous sensors. Since we only exchange timestamps, we can exchange timestamps of previous situations about temperature between sensors of temperature, of rain, or anything. So we are working currently on testing the approach with larger neighborhoods, developing the peer-to-peer architecture, and we work on a very different approach which tries to track the movement of the clouds, considering that each PV system is like a sensor which can track all these the movement of clouds. So it's a different approach because the approach I've described just consider global climatic situation which which are frequent in the past, and this new approach is dynamic and track clouds in real time. So it's a very different approach. So thank you very much.
Thank you for a very interesting talk. So we have time for some questions.
Sounds a very nice idea. I think it's a great idea of changing timestamps. I was wondering, how do you select the top ones in the past for each site? Do you consider just windows of 10 minutes, for example, as you were saying, or do you consider, let me pick the entire best day in the past or the entire best 2 hours? What is the way of selecting those local best in the past?
We use, so we have this template, so it's like a sliding window. Then for each position of this window, we have some values, and we compute the Euclidean distance from the current situation, and then we just take the k most similar. Does it answer?
For a period of 10 minutes, for example?
For
whatever period.
For a fixed number, the template, for instance, the template may be 6 hours. And it's a fixed period. It does not have to be the same length for the different sensors, but for one sensor, it's fixed. So we have tried several values. It depends if it's 10 minutes data or hourly data, and 6 hours is something which gave the best results.
Thank you.
Any other questions? You have another question? Sure.
At some point, you mentioned that you were using weights to decide between those past values and between neighbors. How do you compute those weights? What are those?
We have weights for within each site. We have some weights depending on the distance. So it's normalized and it's just decreasing weight with the distance. But then now from between the sites, we combine the local weights, normalizing them. But we only take, we also have a coefficient which is the proportion of external data, external weights we consider from outside sites. And we can vary this coefficient. So if this coefficient is equal to 0, it means no collaboration. If it's equal to 1, it means that only the other sites contribute to the prediction of the local site. Is it clear? So I can give some details about it.
Yes, a question in the back.
I was curious if there are any seasonalities in patterns of your data or not. I mean, it looks like you don't consider that.
Yes and no. Since it's not very far from the equator, so the days are almost of equal length. There is some seasonality, but the seasonality, the consequence of this seasonality is that we need a minimum of 1 year for learning of history, for finding the neighbors, the analogs, for finding the analogs. Then there was another question, which was since all the days are not of the same length, so how do we manage with this? So we decided to select only the times where there is production all the year. So it means that prediction during the beginning of the day, in summer, for instance, and at the end of the day is not very accurate. We use another system, another approach to do it.
Let's thank the speaker.
Me? Is it okay? So first I want to thank the organizers to give me the opportunity to present this work here. This is joint work from Telecom Paris Tech, which is an engineering school in France, and EDF, Électricité de France, which is the main electric power company in France. So the motivation of this work is that, as mentioned Joao, there is a trend to introduce more renewable energy in the power network, mainly solar panels, PV, photovoltaic PV systems, and wind farms. So this is a problem for the power network because the production of electric power is subject to huge variations with time. As you can understand, if there is sun, there is production by PV system. If there are clouds, the production goes down very fast. So this is related to the smart grid problem. In the smart grid, one important thing is to introduce renewable energy resources in the grid. So there is a need to be able to predict what's going to be the production of renewables in a short term, I mean a few hours, and more locally, I mean in a region or in a city. So the goal is to build here a method, to develop a method for very short-term predictions of individual PV system. I mean here one site of solar panel. There are several approaches to do so. First, the main approaches do not deal with prediction for individual sites, but usually there are methods dealing with a region and a longer term, for instance, prediction 1 day ahead, more aggregated and longer term. And these methods use...
Our next speaker comes from Paris, France. His name is Dr. Georges Berkeley. He's a professor at the École Nationale Supérieure de Télécommunications. Sorry if I didn't pronounce that properly. I don't speak French. He also works for the French National Electricity Company, and he's going to talk to us today about a pretty hard problem to deal with very long time series where you have very wide gaps. And how do you do interpolation? And when you do this interpolation, estimate the error. And this is very relevant to problems we have here at UC Berkeley in astrophysics, because we have very big gaps. And we also have measurement error in our observations. So many of us here are interested to see this applied to a different problem for photoelectric cells, for solar cells. He's going to talk to us about how to predict power generation given variations in sun and cloud cover, and in a sensor network, so that you can sort of share power. A pretty cool project. So I'll give the floor to him. Thank you.
Thank you. Can you hear